So far, we've been talking about isotopes that are naturally radioactive. So let's move on to artificial transmutations and man-made radioactive isotopes. Put your pencils down for now.
You should recognize this equation as a natural decay or transmutation. Uranium is all by itself on this side, the reactant side of the equation. It spontaneously gives off an alpha particle and changes into thorium. But look at this equation. This is a stable isotope of nitrogen. To force it to change into another element, it's bombarded or hit by an alpha particle. The result is that a proton is given off and a new element is produced. See if you can identify it by completing the balanced equation and tell your teacher. The top number is 17 and the bottom number is 8. And you should recognize, because of the atomic number 8, that this is an isotope of oxygen. This was the first artificial transmutation performed by Ernest Rutherford in 1919. Since then, all the man-made elements past number 92 on the periodic table have been produced by bombardment reactions. It sounds easy, doesn't it? Just hit the nucleus with some sort of bullet, such as an alpha particle, and get a new element. But it's not as easy as that. Think about it. The bullet in this case is a positively charged alpha particle with a charge of positive 2, and it has to hit the nitrogen nucleus, which has a charge of positive 7. This means that the two particles repel. And to make larger and larger nuclei, we have to bombard nuclei with even more protons. And the charge on the nuclei of the elements we're bombarding is also greater. So this means more and more repulsions. To overcome these repulsions, the positively charged bullets must be accelerated so that they are going very, very fast when they slam into the target nuclei. This is done with an incredible device called a particle accelerator.
So why don't we use neutral bullets, such as neutrons? It just so happens that two German scientists named Hahn and Strassmann were trying to do that very thing in December of 1938. They were bombarding a sample of uranium with neutrons, hoping to produce a heavier element. Little did they know that they were about to take the first step that would end in the production of a weapon that would forever change our world. To their surprise, Hahn and Strassmann found that when uranium atoms were bombarded with neutrons, one of the products was barium, an element about half the mass of uranium. They were reluctant to believe the results, but Hahn mentioned the experiment to a former colleague who had fled Nazi Germany. Eventually, word of the discovery got to Niels Bohr, and Bohr and others came up with an explanation for what had happened. The atom had been split. This was the first fission reaction. As you watch this explanation, fill in the blanks in your notes.
When a certain heavy nucleus, such as the rare isotope of uranium U-235, is hit by a neutron, the nucleus begins to vibrate. At some point in its vibration, the nucleus becomes elongated like this. Now remember that the strong nuclear force holding nucleons together only acts over a very short range. When the nucleus is stretched out like this, the strong force is weakened. Now the repulsion of the protons is greater than the strong forces between the nucleons, so the nucleus splits into two smaller particles. In addition to the two smaller nuclei, we get 3 more neutrons released, and a tremendous amount of energy is released because the 2 smaller nuclei are so much more stable than the one large one. Here's the equation for the fission reaction. Notice we start with a neutron plus the isotope of uranium. We get 2 smaller barium and krypton nuclei, 3 neutrons, and a tremendous amount of energy. Now, if you look closely, you will notice that the equation balances on top and bottom, left and right. So it looks as if mass is conserved. But it turns out that the mass of the particles produced by the fission reaction is slightly less, won't show up here because of the rounded numbers, than the total mass of the neutron in the uranium nucleus to begin with. So what happens to this tiny bit of mass? How can this be explained? Well, you know that during chemical reactions, matter is neither created nor destroyed, but that's not true of nuclear reactions. During fission, a tiny amount of matter is converted into energy. We can actually calculate the amount of energy using Einstein's famous equation E equals mc squared. When you take a tiny bit of mass and you multiply it times the speed of light squared, you get a tremendous amount of energy released.
Scientists in the United States were shocked by the discovery of fission and the tremendous energy produced. But they were just as impressed by the fact that more neutrons were produced in the reaction. What could happen if these free neutrons went on to hit other uranium nuclei and cause them to split, and so on and so on? They realized that a chain reaction weapon was a possibility, and they were terrified by the prospects of Hitler developing such a weapon. So they sent their most famous colleague, Albert Einstein, to Washington to ask President Roosevelt to fund their own research. Enrico Fermi, who had fled fascist Italy to come to the U.S., was appointed to head a research team to create a controlled fission chain reaction. 6 months later, on an abandoned squash court at the University of Chicago, the first self-sustaining nuclear chain reaction was achieved. The team sent a coded message to the government of this success. The Italian navigator has just landed in the New World. This demonstration will give you an idea of the requirements for a fission chain reaction. First, we've set up the dominoes with lots of space between the pieces. When the first one falls, it does not produce a chain reaction. Remember that atoms are mostly empty space. So in a piece of uranium the size of a pea, almost every neutron that is released by the fission of one nucleus reaches the surface and escapes before hitting another nucleus. Now we'll place the dominoes closer together. When the first one falls, a chain reaction occurs. The minimum mass of fissionable material required for a chain reaction is called critical mass. Next, we'll set up the dominoes as before, but this time we'll remove one piece. The chain reaction slows down. And when enough pieces are removed, the chain reaction stops. In nuclear reactors, fission chain reactions are controlled.
Fermi's chain reaction is the basis for nuclear reactors that furnish energy for nuclear submarines and power plants. I'm going to show you a very simplified diagram of such a reactor. In Fermi's reactor, graphite blocks were used to slow down neutrons enough to allow them to strike unstable radioactive nuclei like U-235. Remember that neutrons are not repelled by the positive nucleus, so they don't need to be accelerated. In more modern reactors, water is used instead of graphite to moderate or slow down the neutrons. Now, rods containing the fissionable material like U-235 or plutonium are inserted into the reactor, and a slow-moving neutron starts the chain reaction. To keep the chain reaction from getting out of control, we use control rods, which are inserted here. These rods are made of boron or cadmium, which absorb neutrons. When the control rods are all the way in, they will absorb enough neutrons to stop the chain reaction, just as removing some of the dominoes stop the rest from falling.
The tremendous energy released by the fission reaction can be used to make steam to run turbine generators, which produce electricity. At present, about 10% of the electricity produced in the United States comes from nuclear power plants. Now, there are two dangers from nuclear reactors. One is the radioactive byproducts of fission, called nuclear waste. Since nothing can be done to make these byproducts harmless, they have to be stored safely and permanently. The other danger is meltdown. cooling systems and backup cooling systems, like these water cooling towers, must operate constantly to control the heat produced by the reactors. If the cooling system fails, as it did in Chernobyl, the reactor equipment can overheat, melting and releasing radioactive materials into the air or even into the water table. Now, that's a serious danger, but an accident at a power plant will not produce the same explosion as an atomic bomb. To produce that kind of explosion, critical mass won't do. You need supercritical mass, where atoms are packed in so tightly that once fission starts, it is self-sustaining and cannot be stopped. The race to make such a weapon before Hitler could do so involved 5 years of frantic work for American scientists and engineers.
Getting from that first chain reaction to the bomb was the task of a secret program begun in 1941 called the Manhattan Project. In 1942, Robert Oppenheimer was made the director of the Los Alamos lab. And in 1943, he assembled 200 of the best scientists in the field to live and work there. Their task was to design the bomb itself. 2 other secret cities were built in Tennessee and Washington to house scientists whose task was to extract U-235 and plutonium from non-fissionable uranium ores to fuel the bomb. On July 16th, a test bomb was detonated at a site called Trinity in the New Mexico desert. An intense flash of light was seen by observers in the bunkers 10 kilometers away, and a fireball expanded to 600 meters in 2 seconds. It boiled up in the shape of a mushroom. 40 seconds later, a blast of air along with a deafening roar of sound reached the observers. After Oppenheimer witnessed the explosion, he said, "We knew the world would not be the same. The nuclear age had begun."
In addition to releasing energy by splitting heavy nuclei, scientists have found that even more energy can be produced when small nuclei are combined. This is called fusion. A fusion reaction releases up to 10 times the energy of fission reactions involving the same mass of reactants. And, unlike fission, fusion happens naturally. Tell your teacher where. Yes, nuclear fusion powers the Sun and other stars. Scientists believe that the Sun, a typical star, started out as mostly hydrogen gas, which condensed under the force of gravity. When the pressure became great enough to heat the gas to around 15 million degrees Celsius, hydrogen atoms began fusing into helium, and the Sun began to shine. Scientists believe that the Sun is about 4.5 billion years old and is about halfway through its life cycle. Time to get some notes on fusion.
Fusion is the combination of 2 very small nuclei into one larger one with a huge release of energy. Here's one example of a fusion reaction. In this reaction, 2 different isotopes of hydrogen, deuterium with a mass of 2 and tritium with a mass of 3 atomic mass units, combine to form a helium nucleus and a neutron. Neutrons are not always released in fusion reactions, but energy is always released. Scientists have determined that the mass of these 2 isotopes of hydrogen are quite a bit greater than the mass of the one helium and the one neutron. This mass is converted into energy, again according to Einstein's equation, E equals mc squared.
Can we duplicate the fusion reactions of the Sun on the Earth? The answer is yes, but with a catch. Prior to the development of the A-bomb, we were unable to attain the high temperatures necessary to make nuclei fuse. But the temperature of an atomic bomb explosion was found to be about 5 times the temperature of the Sun. So the fission reaction of an A-bomb could be used to detonate a thermonuclear or fusion bomb. The first hydrogen bomb was detonated in 1952. An H-bomb has never been used as a weapon, and hopefully it never will be. So how do we go about controlling a fusion reaction for constructive purposes, and why would we want to do so? Well, The Earth's oceans contain enough deuterium and tritium to furnish vastly more energy than all the world's fossil fuels and fission fuel. And fusion reactions don't produce radioactive byproducts. But the challenge is producing the high temperatures required, and doing so without vaporizing all the materials and equipment. You might want to read about how scientists are trying to develop non-material containers. Phew, it's really hot up here. I think I'll go back to the nucleus. I find it absolutely amazing that something so small holds so much power. There is so much more to learn about nuclear science, but we simply don't have the time. I do hope, however, that you've learned enough to develop some informed opinions about the advantages and disadvantages of nuclear reactions. As for me, right now I'm going to take another tour of the nucleus.